Welcome to Maths with EJD. In this video, I continue with vectors as I talk about vector components. Vector components. Okay. Vector components. First of all, let's start with the idea of unit vectors. I referred a lot to unit vectors IJK I think in the second video of vectors. So here, let's talk about it. What is a unit vector? A unit vector, a unit vector is a vector with a magnitude of 1. It's a magnitude of 1. Of course, unit means 1. So it's a vector with a unit of 1, with a magnitude of 1, and it is used to specify direction. So unit vectors are fundamental. Unit vectors are fundamental in vector analysis. Because they allow us to express any vector as a product of its magnitude and direction. So in Cartesian coordinate system, anytime you hear about Cartesian, it's simply talking about the X and Y, X, Y, Z axis. So in a Cartesian coordinate system, so we see that the unit vector I, this I actually represents the unit vector along the X axis. So I is the unit vector along the X axis, and J represents the unit vector along the Y axis, while K represents the unit vector along the Z axis. That, of course, Z is included if you're talking about 3D space. If you're talking about 2D space, you just have I and J in the X and Y axis respectively. But for three-dimensional space, you have I, J, K in the X, Y, and Z axis respectively. So let's look at some examples. So imagine this example for a vector V, which is equal to 3i plus 4j all right? The magnitude, of course, we did some things on magnitude in the previous video. So the magnitude of V is given as the absolute value of V, the absolute of vector V, which is the square root of each component of the unit vectors. So that's 3 squared plus 4 squared. That means the magnitude of V is square root of 9 plus 16, which is square root of 25. And that is simply 5 units. So that is that. So that is the magnitude of the vector, right? Now, let's talk about the corresponding unit vector. So the corresponding unit vector, V. Now pay attention. The unit vector has a cap, whereas the vector itself has an arrow. So the corresponding unit vector V is expressed as follows. It is actually the unit vector, which is equal to the vector V itself divided by the magnitude of the vector. That means the vector itself is 3i plus 4j divided by the magnitude, which we have found to be 5. So that means you have 3 over 5i plus 4 over 5j, which is the same thing as 0.6i plus 0.8j, like that. So the unit vector v hat is actually the unit vector v hat points in the same direction, as vector v itself, but has a magnitude of 1. Okay. Now, if we have to do something in 3D space, we can also do that. So in 3-dimensional space, for a vector u, which is the same thing as 2i minus j plus 2k, the magnitude is the absolute value of u, which is equal to square root of each component. That is 2 in the component, or in the I direction, that's 2 squared, plus in the j direction, that's actually minus 1 squared. So, you have the component 2 minus 1, 2. So here we have the square of each, the sum of the square of each, and then we take the square roots. So we have 2 squared plus minus 1 squared plus 2 squared, so that the magnitude of vector u is now equal to square root of 2 squared is 4, minus 1 squared is 1, 2 squared again is 4. 2 squared is 4, and then we have the magnitude to be square root of 9. That means the magnitude of vector u is actually 3. So the unit vector now, the unit vector in the direction of u, of the vector, in the direction of vector u, is now this: u hat equals u vector over the magnitude of u, which is 2i minus j plus 2k all over 3. So that means we have, that is 2 over 3i minus 1 over 3j plus 2 over 3k. So, and that is approximately 2 over 3, that's 0.67i. Then minus 1 over 3, that's minus 0.33j. Then plus 2 over 3, that is plus 0.67k. So that's the unit vector of that vector u, which is 2i minus j plus 2k. So having taken care of that, let's talk about resolving vectors into components. Resolving vectors into components. We are talking about component vectors. So how do you resolve vectors into their respective components? All right. So resolving a vector into its components involves breaking it down, breaking it down into vectors that lie along the coordinate axis, the coordinate axis. So this process is crucial. This process is crucial for simplifying vector calculations, especially in physics, and engineering, where forces and other quantities are often analyzed in terms of their components. So if we take a 2D example, so let's talk about a 2D example first of all. So if you have a two-dimensional example, suppose you have a force, vector F. You have a force vector F with a magnitude of 50 Newton, acting at an angle of 45 degrees to the horizontal. Of course, the horizontal is the x-axis. So if we have that, right, that means we have something like this. You have this. So this is the x-axis, and then you have a 50 Newton force at angle 45 degrees to the horizontal. Okay, so so one thing is that you can actually bring this down, so that you have this is the vertical component. Of course, this is the y-axis. So this is like the vertical component f of y, and this is the horizontal component f of x. So we can resolve this 50 Newton force. We can see the force to be exerting in the vertical direction and the force to be exerting in the horizontal direction. So if we look at f of x now, which is the x component, so first, right, to resolve f into its components, so that's what that's what we want to do. And then we have the x component. So we say the x component f of x is, okay, I mean, I can just go straight. The x component f of x is actually the same thing as, so you can see that if you have it, it's more like you have a triangle now. You have this triangle, 15 Newton. This is a right angle. You have 45 degrees, and this is f of x, the x component, and the y component f of y. So this is, of course, this is adjacent. This is opposite. And this is the hypotenuse, right? So the x component actually is more like, okay, the x component f of x, right, is actually, okay, let me do that in that corner. So if you want to find this is adjacent and hypotenuse. So what combines adjacent and hypotenuse together is cosine. So you have cosine of 45 degrees. is equal to adjacent f of x, hypotenuse 50 Newton, right? So that means that cos 45 degrees, I think it's better if I write it straight. Okay, from what we have there, right? So I think let me just do it neatly here. In fact, let me draw the whole diagram out so that it can make more sense. Okay, so now we have, so if we bring that portion out, right, we have horizontal axis, we have that may not be accurate. This is 45 degrees, this is 50 Newton, this is f of y, the vertical component, the y component, and this is the horizontal component, f of x. So here we can see that for let me just say for f of x, for f of x, for f of x, what do we have? We have adjacent, we have hypotenuse. That will be cosine. So it means that cosine of 45 degrees is actually f of x over 50 Newton. So if you cross multiply, f of x times 1 is actually f of x, and that is 50 cosine of 45 degrees. And I think 45 degrees is 1 over root 2 or something. Yeah, it's 1 over root 2. So f of x now, fx rather, is 50 times 1 over root 2. If you rationalize, that would be f of x equals 50 times 1 over root 2. Because this is surd, right? We can rationalize. That will be root 2 over root 2. Yeah, it's more like we're multiplying by 1, so nothing is really changing. So that f of x is 50 root 2. Root 2 times root 2 is actually 2. So that means that f of x itself, fx itself is actually 25 root 2 Newton. Of course, you can punch your calculator to get that. Root 2 is 1.4141414141, like that. You can multiply by 25, or you can leave it this way. So you see that if you are exacting a 50 Newton force 45 degrees to the horizontal axis, it means that in the actual horizontal axis, the force that will be exerted along this line, this horizontal line, would be 25 root 2 Newton itself. Okay, so let's talk about the f of y, for f of y now, for fy rather. So fy, this is opposite, and then in connection with the hypotenuse, so you have sine, opposite over hypotenuse. So it means that sine 45 degrees is equal to fy over 50. So if you cross multiply again, that's fy equals 50 sine 45 degrees. Again, sine 45 degrees is also 1 over root 2. If you check trigonometry, I explained how this can come about. And of course, you can punch your calculator for this. But I mean, 45 degrees is a special angle, so you can always get it in third form. So sine 45 degrees again is 1 over root 2. Then if you do the same process, you have 50 times 1 over root 2 times root 2 all over root 2. That's us rationalizing the third. So we don't have a square root at the bottom. So we have 50 times 1 times root 2. That's 50 root 2. Root 2 times root 2 is root 4. And root 4 is 2. So that means, again, we have, so in both fy now is, again, 25 root 2. It doesn't always have to be like this. It can be different, actually, but this is only special because it is, that's what we have here. So it means the force exerted in the vertical direction is also 25 root 2 Newton. And of course, you can punch your calculator to also get that. So in all, we can say that, so the vector f, the vector f, the vector f can be expressed as f, which is equal to 25. Okay, well, let me just go through the motion. So you have fxi. Normally, I think, yeah, all these are vectors too, right? All these are vectors. Don't forget, they are vectors. Never forget the arrow. If you are typing, you make it bold. You can make it bold or use the arrow still. So do what's suitable depending on what you're using. Okay, so these are vectors, so don't forget to put the arrow so we can know they are vectors. Yeah, all this, like that. So of course, we know f itself is fxi, fx in the I direction plus fy in the j direction, so that at the end of the day, we have f like this equals 25 root 2 I plus fy 25 root 2 j. So the vector f can be expressed as that in these two components. Of course, all of that is in Newton. So all this in Newton, because we're talking about force here. Okay, so we can do the same thing in the in 3D in 3D space. So what we have just done is a 2D example. Let's do the 3D one. Say that so let's say 3D example. 3D example. So we have for a vector r, for a vector r with a magnitude of 10 units, magnitude of 10 units at an angle of 30 degrees with the x-axis, 45 degrees, 45 degrees with the y-axis. You know, we are talking about three-dimensional space now. So 45 degrees with the y-axis, and 60 degrees with the z-axis, The components, the components can be calculated, as so. Of course, we have the first part, 30 degrees, 10 units at an angle of 30 degrees x-axis. Then we have 45 degrees with y-axis, same 10 units with y-axis, and then we also have 10 units that is at 60 degrees with the z-axis. So we can simply calculate all of that as follows. That Rx is simply the R itself cos 30 degrees, that's 10, and cos 30 degrees is root 3 over 2. That is simply 5 root 3 Newton in the direction of the x-axis. Then you have Ry. Ry will be R itself. The angle is 45 degrees. That's the second one. So cos 45 degrees. Again, we have 10 times 1 over root 2. And if we do what we did before, that's 10 root 2 divided by 2, which is 5 root 2 Newton for that. You know, we've done this 1 over root 2 thing a lot. And then lastly, we have RZ. RZ is R cos 60 degrees. R cos 60 degrees. So here we are using cos all through, so that so because we are in 3D space, so R cos 60 degrees is equal to 10. Cos 60 is 1 over root 2 actually, so that's 5 Newton in the direction of in the z direction. So we can say thus the vector r, okay, don't forget all this. Thus the vector r can be represented as r equals rxi plus ryj plus rzk. So r now is actually rx, that's 5 root 3 I plus 5 root 2 j plus 5k, like that. So that's how to resolve vectors into their components. Okay, so let's do one more thing, which is also important. Let's go for calculating magnitude using components. How do you calculate the magnitude of a vector using components? So you know the other time we get the magnitude and the direction, and then we resolve into components. How about taking it back to where we started from? That's what this part is about now. So we have calculating magnitude using components. So you have a vector that are in its components. So we want to get the overall magnitude. Calculate magnitude using components. So the magnitude of a vector, the magnitude of a vector is the length of the vector, the length of the vector, and can be calculated using its components. Can be calculated using its components. So in 2D and 3D, two-dimensional and three-dimensional spaces, okay, this is done by applying the Pythagorean theorem, the Pythagorean theorem, Pythagorean theorem to the components, okay? Of course, I mean, we've been talking about 2D, 3D all this while. In case you don't, it's new to you. When we talk about 2D, that's two-dimensional space. That means we have x-axis. Of course, this is two-dimensional space. X-axis, you have the origin, you have the y-axis. This is two-dimensional space. Then for three-dimensional space, it's something like this. I'll try as much as possible to get a proper presentation. So let's say here now you have y, this is the x-axis, right? This is the y-axis. Now each axis is actually 90, all the axes are orthogonal, so they meet at 90 degrees to themselves. So because this is three-dimensional now, we can have something like this. So this is not like the z-axis. So they are mutually orthogonal, meaning they are all at 90 degrees with themselves. So this is what we mean when we say 3D. This is three-dimensional, this is two-dimensional. Okay. So that's just to be sure that is clear to everybody. So let's take examples in both 2D and 3D. So let's start with a 2D example. Example in 2D. So consider vector C, which is 6i plus 8j. So here, straight, the magnitude is the absolute value of the vector C, which is square root of cx squared plus cy squared. Of course, this is cx and this is cy. Okay. So that means we have square root of 6 squared plus 8 squared, which the magnitude is now square root of 6 squared, that's 36. 8 squared is 64. So that the magnitude, of course, absolute value, that is 100, square root of 100, and C itself is actually 10 units. 10 units. Okay. So that's the magnitude. Of course, if you want to get the direction, don't forget that will just be theta, which is equal to arctan of cy over cx. So again, theta would be arctan of cy already, you know that to be 8 So you have 8, you have 6. So theta is equal to arctan of 4/3. And you can punch your calculator to get that. Okay, let's take an example in 3D. Example in 3D. Example in 3D. So for an example in 3D, so if you have a vector for a vector D, which is equal to 3i plus 4j plus 12k. So the magnitude is absolute value of D, which is equal to square root of dx squared plus dy squared plus dz squared, because this is dx, this is dy, and this is dz, like that. So that means absolute value of D is 3, 4, 12, right? 3, 4, 12. That's 3 squared plus 4 squared plus 12 squared. So that this is absolute value of D. This is square root of 9 plus 16 plus 144. So that everything is, so 9 plus 16 is 25. 25 plus 144 is 169. So the absolute value of D is actually 13. That's 13 units, if you please, that whatever the dimension is. So these calculations, these calculations show how the magnitude is determined by the contributions from all components of the vector, So the magnitude of a vector, of a two-dimensional vector, is determined by the two components. For a three-dimensional vector, it is determined by the three components of the vector. So understanding this concept is fundamental for analyzing vector quantities in physics, engineering, and other fields that involve multidimensional space. So in the next video, I'll be talking about vectors in geometry and physics. See you then. Thanks for always stopping by. If you have not subscribed, be sure to do that. Hit the subscribe and hit the notification bell so you can always get alerted when time a new video is released. Also, be sure to comment, like, and share so that more and more people will get to learn. See you. Bye.